Hi, good afternoon, everybody. I'm going to talk about experimental study of interference models for low power wireless networks. It's an interesting study. It's done on the sensor network platform. The reason why we use the central sensor network platform over here is not because we want to do a sensor networking research, but because we want to get a radio which is completely programmable, and we can choose whatever MAC protocol we want and program it into it, have complete control over everything on the radio. You can switch off carrier sensing, you can switch off all kind of overheads MAC protocol might have, like backoffs, and we also have control over changing the power level, transmission power level, changing the channel dynamically, and anything you can think of. This platform is basically the crossbow modes, actually the Berkeley modes, and it's the newest generation, the Telos B modes, which has a USB interface and a Zigbee compatible radio, although they don't have any Zigbee MAC implemented on it. So the study was basically for a multi-hop TDMA scheduling protocol. Typically what happens is that in a multi-hop TDMA you would transmit from more than one location, so there would be more than one transmitters just to get the spatial reuse, because there could be a transmission in one end and another transmission on another end because they don't interfere. The problem is to find out such pairs or sets of transmitters that do not interfere with each other. The reason why we want TDMA and why do we want to schedule more than one transmitter at a time in the same slot is because we want to get the maximum throughput by using spatial reuse. Now, most of the existing solutions, if you would be aware of in network simulators and everything, they use a unit disk model in which two links do not interfere if they are within a certain, beyond a certain distance or beyond a certain number of hops from each other. The problem is that this kind of scheduling, in which it's an approximate notion of interference, it might be inaccurate. If it is too aggressive, there might be actual interference in between them, or it could be too relaxed, so you're not really using much of spatial reuse as you could, so you're not being able to use the maximum bandwidth which you would otherwise. They're approximate models, and they approximately model the real interference in the real actual wireless network. And as I said, they might either produce very sparse schedule, or they might produce very dense schedule, depending upon how aggressively you use those models. Now, this is how a distance-based model would look like. You see the middle one, there's a receiver over there. Anything within a distance d from that receiver is the receive range. Anything beyond that and within a distance 2d would be the interference range. So if you look at this, only one transmitter within the receive range is allowed to transmit, and all transmitters within the interference range should also be quiet. Otherwise, there would be an interference at the receiver's end, and the packets might not be delivered correctly. So that is an assumption of the interference graph in a distance-based model. So it basically assumes that at a distance d, the signal-to-noise ratio is less than the threshold, and that's why it's okay to transmit, or it would be a receive distance. Now, similarly, a hop-based model, there is a one hop-based model which says that if the transmitter is within one hop from the receiver can receive the packet, but if it is beyond the one hop, it would not, the receiver would not be able to receive anything. So this is the receive range. This region would be the receive range for the receiver. Now the solution which I was working on was to develop a practical measurement-based methodology so that we can get a more realistic interference model in wireless networks. And then further, the goal to develop this model is basically to predict the probability of successful packet reception given this model, and can we actually predict, or how easy it is to predict such a model, such a packet reception rate. Now then we want to also compare how accurate the model which we are developing using measurement-based techniques would that be as accurate or more accurate than the models which are being used, or how much is the variation in accuracy? Basically to see whether we really need to do all these measurements. Are we getting enough substantial benefit by doing the measurements, or is it just a marginal benefit, and so we might as well use an approximate model. So overview basically of the physical interference, the model which I'm trying to measure and model over here. There is the signal component in wireless communication, there is a noise component, and then there is an interference component, interference between transmitters which are transmitting at the same time. Now these three components, we know that they play together to form the signal to interference and noise ratio. And from the classic or basic theory of wireless communication, we know that there is a relation between the successful packet delivery rate and the SINR. And typically SINR is proportional to, PRR is proportional to signal divided by noise plus interference. We also know from a basic theory that PRR is equal to 1 if SINR is greater than a certain threshold. And that is basically the model which all the distance-based and hub-based interference models use. They say that approximately at a certain distance, this SINR is it falls below the threshold, and that's why it's not good to transmit, and that's why that distance d becomes the approximate cutoff point beyond which the transmitters, if they transmit, the receiver would not receive anything. Now this model which I'm talking about over here is known as the physical interference model, and this word or this term was originally coined by Gupta and Kumar in one of the papers in, I think it was in Moby Hawk 2006. And the basic goal for this whole measurement technique is to find out, can we experimentally model this relationship? We know that the relationship exists, and we know it through measurements on signal analyzers and oscilloscopes and everything. But can we actually model this relationship using radios themselves? Because if we can do that, then these radios would be able to use the relationship to develop or follow a protocol which is based upon this model instead of using the approximate model. So the question is whether can we really model this relationship experimentally. So first step to see over here is that the I in SINR is that additive. Because we are dealing with a multi-hop TDMA scenario, it's no longer just one interferer, it could be multiple interferers. And so we want to know if this I is actually a sum of all the interferences we are seeing in the area. So let's say for K simultaneous transmitters, is it possible that, is it true that I total is equal to the sum of all the I's? The next step is, can we compute and predict packet delivery rate if we have if we know the SINR value for a set of links. So let's say we have a set of links that are transmitting simultaneously, and we somehow find out what is the SINR going to be at each of the receivers. And then can we say for sure that since this is the SINR, the PRR would be X, Y, and Z? So that is one of the interesting questions, and given if we have an answer to this question, then we can certainly say that it will be useful for a higher layer protocol, for example a scheduler or a medium access protocol, and even a routing protocol to make a decision about how to proceed in transmitting the packet to the destination. We also want to see how this model which we are developing with so much work would be useful to us, in the sense that does it compare equally with the other models, or is it much superior? Is there any value in doing these experiments and using these models, or it was okay to just use whatever we had before? So let's go ahead and see how we do the measurements and what are we going to do to find out. The first step, as I said, was to find whether the joint interference or joint signal strength, which is I total, was equal to sum of the individual interferences. So now since all the transmitters are transmitting simultaneously, I don't know what each of the seconds, and there is also an indication register telling you whether it's valid value or not. So if the value is valid, then you basically record. Okay, so since you're measuring it 10 milliseconds, it's possible there was no transmission going on. Now you can avoid that by looking at the curve itself, because you would see if you draw the graph, a spike when there was a transmission, and you would see lower spike when there's no transmission. So obviously we can filter out those values in which there was no transmission.
So when you say I received a packet, only if you get a complete packet you have received a packet.
Yes. Yes. Also notice that when the base station is sending the command to all the nodes, it's actually telling the nodes about their transmission schedule. At the same time, the receivers know that it's the receiving schedule. So they're basically measuring the signal strength more often during the receiving schedule. So because the nodes are aware that there would be a transmission going on at the time. So we do that with all pairs, and we measure joint receive signal strength and packet delivery ratio. Notice that some of the nodes over here would receive packets from node B, and over there they would receive packets from node C. This is not a real scenario. I mean, this is one of the examples.
So how long are the schedules? The base station tells in this slot you have to receive, in this slot you have to receive.
So in order to avoid all kind of time synchronization problems, what I did was for each packet to be transmitted, the base station would send a command. As soon as you receive the command, you have no carrier sensing, so you know you start transmitting at the same point, right? So basically everybody is transmitting at the same time. For every packet, the base station is telling you to transmit. So you do that 1,000 times to get 1,000 packets. So it's not, so if you use a TDMA schedule to do that, then it's possible that there's a time drift, right? And then your measurements might be in error. Because we don't want any measurement error over here. We are doing measurements so that we can get an accurate model. So that's why for every packet to be transmitted, the base station would send a command, and the transmission would happen. All the measurements would take place. It would send another command, and this would happen for like 1,000 packets or so. So that we have a statistically large data set to compute an average from, right? So it's not like one schedule and everybody transmits, and at the end you are done, because you want to avoid all kind of time synchronization problems in there.
So
Did I answer?
If you
Yeah.
want A to transmit half the time, 60% of the time, and B to transmit 40% of the time. How do you do this?
We don't do that. They're transmitting together at the same time, because we're trying to get the joint signal strength over here. So we're not doing a TDMA over here. We're doing just the signal strength measurement over here. So that's why when they're transmitting, they're always transmitting together. It's not 60-40. Sure.
Another question. You said that you sample RSI every 10 milliseconds?
Yes.
So what is the size of packet you're sending, like in terms of time it stays in the air?
I think I forgot that number, but it was around 13 to 15 milliseconds.
Okay, so you're sampling at least once in a packet?
Yes, it is. Also, not just that, but when the schedule actually goes to the network, the receivers start sampling more often at that time, because they know that there will be a transmission at this point. So as I said, we do this for different pairs, and then triplets, and 4, 5, up to 6 interferers or transmitters. After doing that, what we get is a nice graph in which we plot the measured JRSS, the measured being the one when more than one transmitter was transmitting, and the estimated, which is the sum of the transmitters, some of the interferences when the transmitters were transmitting individually. So for example, when A and B were transmitting alone, we would get signal A and signal B, and we would add that up and plot it over here. And if A and B were transmitting separately, so A and B was transmitting together, we would get the measured JRSS, we would plot that here. So this was the measured and this was the estimated, and this particular curve is for 2 simultaneous senders, and that one is for 6 simultaneous senders. So and then I draw a straight line, which is y equal to x, just to see how close the estimated and measured are with each other. Ideally, they should all lie on this red line over here, but as you see, they're very close, and the R square value, the coefficient of determination, was 0.97 for that curve and 0.95 for this curve. So it's basically pretty accurately, I mean, we can very accurately say that joint interference is actually sum of the interference, individual interferences.
So this is RSS across all receivers, right?
All receivers, all receivers who receive those packets for all pairs of transmitters. So this is basically all pairs, because there are two transmitters, so all pairs of transmitters, and whoever received the packet would do the measurement in both ways, in both axes.
Right, so what was the spread for a given receiver? I'm assuming that you didn't get a constant value for, say, 1,000 packets transmitted.
Actually, the values were pretty consistent.
Pretty consistent.
Yes, so that is why we moved on with the experiments. Otherwise, we would say, okay, this is not even consistent. Then what's the point?
So question: when you say RSSI, are you defining it as an integral over the packet duration, or is it sample, value, or?
It's basically averaged over every 10 symbol period in the radio. So if you get
10 symbol period.
Yes.
So, but each symbol period you have only one sample.
Yeah. So, but the radio, the lower layer phi is taking care of that. It's taking 10. Yes, for each symbol there is one value, and it samples it for 10 symbol periods. That's when you get the first valid RSSI value.
So after averaging.
After averaging it, and then as you move on, you keep sampling over 10 symbol periods, and you keep updating the signal strength in the radio. Okay, so the conclusion here was that GRSS estimated GRSS was same as measured, and therefore we can definitely say that we can basically add up all the I's in the SINR ratio. Now, the next question is, can we sample this? Can we model this equation where signals where PRR is equal to a constant multiplied by signal divided by noise and RSS? So the way we do this is, when we're doing the first round of measurements for each receiver and transmitter pair, we are getting a signal strength, right? So we save that, right? And then when we, from the round 2, when we have more than one transmitter, for each pair of transmitters or triplets of transmitter, quadruples transmitters, we know what is the packet received rate for each receiver which received the packet. Those who did not would be 0. And then we measure noise when there is no transmitter. So basically all the nodes are simply sampling their RSS registers in the radio, and there is no transmission going on, and that gives us the noise floor in the environment, and we found that it remains pretty constant during the experimental period. And then we take that, and we know from step 1 that interference is additive, and then we plot the graph, obviously, PRR versus SINR, and this is how it looks like. This was 3 simultaneous senders, and that was 6 simultaneous senders. So it's like an inverted Z. What does it tell us? Obviously, it gives us the indication that there is a connected region for any SINR value greater than 5 dB, which is the threshold we always talk about. We get a perfect packet delivery ratio. We get all the packets received. There's a transition region where we don't know what's happening. It's really probabilistic whether we will receive 10 packets or 20 or all. And then there's a disconnected region which is less than -3 dB where we don't get anything. So we do have a model now, and we want to see how this model works for us. Now when we want to predict what is the PRR, let's say we are given the SINR and we know this is our model. Now how do we know for a given SINR what is the PRR? We cannot just get into, we haven't done all possible SINR versus PRR measurement. It's not possible. There are infinite numbers of PRR and SINR values. So we have to do some kind of approximation. So what we do is we divide the regions into different, it was a 0.1 dB areas, and then we average out all the packet received ratio, and that's how we predict what would be the PRR if SINR was within this range. So that's the SINR range, and we get the average PRR, which is the red line over there. So that's the red line, which basically tells me if whatever the value of SINR, let's say if the SINR was here, we would say, okay, so this would be a PRR value.
So the red line was some curve fitting?
Yes, it was a curve fitting. So now we need to use this model to find out a TDMA schedule and see if that actually is true or how accurate that schedule seems to be. So one way to do is just use a centralized greedy algorithm and feed the model into the scheduler, and you see the scheduler would spit out a set of links that are compatible and can be scheduled simultaneously. When we did that, what we got was a perfect accuracy. Basically we computed the schedule and used that schedule into the network. So we did the experiment on the network itself to see, okay, this is my schedule, and does it work for you? Does it work for the test bed? And it did. It worked perfectly, and we got 100% packet receive ratio. Well, that ends the experiment, and we have nothing else to do.
So in this here, I again want to know. So if the schedule is such that 40%, 60%.
Again, to keep things simple, the schedule basically meant that the schedule was basically which transmitter will transmit in this slot. That's all. So you're basically hard coding, or rather telling the nodes that, okay, this is your slot, this is your slot, this is your slot, and everybody knows what the slots are, then they start transmitting.
So slot by slot, the base station tells who are the transmitters.
Each slot, the base station keeps telling who are the transmitters, and they start transmitting.
And when you say perfect accuracy for all schedules, what do you mean?
What I mean is that whenever a transmitter was transmitting, the intended receiver got 100% of the packets. Okay, so basically when you're scheduling the links, the sender-receiver pairs, right? So perfect accuracy means that the receiver actually got everything which the sender sent. Am I making myself clear?
So what was the rate of transmission?
What do you mean?
The rate in the sense of 5-layer rate, like 6 Mbps or...
Oh, these are 250 megabits per second, 250.
So that's constant, that's it?
That is constant.
And it's working at 2.4 gigahertz.
Yes. Now, the thing is that, okay, we got this perfect schedule, but it's not very useful to us. The reason why we're getting the perfect schedule is because the algorithm will not give you imperfect schedules to try because it knows what are the interference criterions, and it's choosing the links based upon the criteria. So, and it's not very interesting for me because my goal was to find out whether I can predict accurately or not, and that's why I want to predict whether the not so perfect links can be predicted properly or correctly. Yes. How frequently the prediction? The prediction is just a one-time thing. So you're predicting it, and you're creating a schedule and putting it into the network, and that runs for 1,000 packets, and you're done.
So you didn't tell the inner details of the scheduling algorithm. Basically, you just say it's centralized greedy. What kind of scheduling? I mean, maybe if you put more constraints, your scheduler won't give you such set of only connected regions in the link.
Right, but basically to the schedule you will say that, okay, schedule links in which SINR would be greater than beta. You're telling that to the scheduler. The scheduler picks the first link. You give him a list of links, picks the first link, puts it into the schedule, and then goes on to find the next link for which the SINR is greater than beta model will be satisfied. So in that way it keeps picking links from the list of links. Okay, so that's how it spits out the schedule.
And your beta was very high value?
No, it was the 0.5 dB which I mentioned in the graph before. This value right there. So 5 dB. Yeah, so if I told my scheduler that, okay, give me all the links which are greater than 0 dB, so it would give me those links, but then again that was not interesting. I'll tell you what was the next step we did to make it more interesting. What I want to model is what I want to find out is whether I can model links which are not perfect, which won't be perfect if they're scheduled together. So what we did was we took random sets of links. Of course, they were satisfying the primary interference. That means the sender and receiver were not the same. So it was at a given time slot, if somebody is receiving, it would not be sending at the same time. So the primary interference criteria was satisfied. So, but otherwise, it was a random set of links picked out from the test bed and scheduled together in the same slot. So we can expect a whole lot of other things. It was possible that these schedules wouldn't work at all. It's possible that all of them are perfect. It could be a mix. So taking that, now we take the set of links which we scheduled and feed that into the predictor to find out what the predictor says about the packet receive rate, right? So instead of asking the predictor to give me perfect links or perfect PRR, I'm asking the predictor what would be the PRR if I give you the links, okay? And this is how it looks then. And then we compare it with the one-hop based protocol model and range-based or distance-based protocol model. So notice that about 90% of the links have more than 0.25 errors, right? Which is not great. I mean, it's a good thing because it compares pretty well with the other protocols, the other models. We do have a very high accuracy compared to others, but it's not the best possible accuracy. I mean, if you're doing so many measurements, you really want a much better accuracy in your prediction. So we're really not predicting as well as we would want to, although we are predicting better than others. So now we need to find out why aren't we predicting so well. So for that purpose, what we are doing over here is we revisit the model. We see that the model has a connected region where we can actually say with 100% probability that if you have more than 5 dB SINR, you would have a perfect PRR. Also in this region, we can say, okay, you have a 0 PRR if you're less than -3 dB. The problem is this region where the prediction is very probabilistic. We don't know what can happen, right? So given that there are these 3 regions, we take this curve, the red curve, and break that into different regions, or all the 3 regions. So basically what we take is from each set of the links, we find out which set lies in the connected region and which set lies in the disconnected region, and we separate it out from the transition region. In doing that, what we see is that, look at the green curve, it's basically signifying all the links that are in the connected and disconnected region, and we have a very good accuracy over here. This was when all the curves were, this is the same curve as the one I showed before. And this is a set of links which are in the transition region, which is in between -3 dB and 5 dB. And interesting that here the accuracy is really poor. It might be because the way we're predicting it is bad. We're just doing an average over regions. There could be a better mathematical model to make a better prediction over here. But it's really very hard to predict, and it would probably be a separate form of research in information theory or something like that to find out how to predict this region.
So all you're saying is most of the links are either in the connected region or disconnected?
Yes. So the green curve is saying that either it's connected region or disconnected region, right? And the blue one is only in the transition region. So we got the.
You really want to distinguish your model from what already exists in simulators, and
Yes.
you should be worried about the transition region. Right? It's like the connected and disconnected are
Right.
just perfect regions.
So that's what we did. So we basically see if so those are perfect regions, right? But are those perfect regions modeled correctly by the other models? They're not. So this is the set of links which are only in the connected and disconnected region, and we see that we get a very high accuracy with our SINR model, but the distance-based and hop-based model predict much lower PRR, because these models are basically very conservative in scheduling packets together. If you make them more and more aggressive, then they will probably come closer. But still, because they are approximate model, even though you make them aggressive, they'll tend to make more and more mistakes, right? So that's why, because it's really it's not as simple as a unit disk graph. The wireless communication is much more complex, and that's why it's not a truly realistic network if it does a distance-based model for scheduling transmission. So here we show that, okay, even though I'm choosing the links which are only in the connected region, I'm getting a much higher accuracy, but the hop-based and the range-based model, they still predict something wrong.
So for the range-based model, the lowest curve you have here,
Yeah.
even if you take the same threshold as you get from your experiments, you still get a difference in performance, like the 5 dB plus 5 dB?
It is the same threshold, and the reason why, so basically so in order to get the parameters for this, we need to do a measurement to see how much is the distance for a 5 dB receive signal strength, right? So we take that distance,
Okay.
right? So that is the distance used here. And that same distance is used as the one hop distance. You have any questions?
No, what I don't understand is that if my SINR is fixed in both the models,
Yes.
and in both the models, greater than that SINR means a good link, a perfect link.
Right.
And where is the difference?
The difference is basically this model is not using SINR really, it's using distance.
That's fine. You can have various models of distance based on distance,
Right.
which at different distances give you a certain SINR. But once I know what my SINR is, what's the difference?
Well, so the difference over here is it's not using the SINR. It's saying that, okay, at this distance I would have a perfect link. It's actually not factoring in the interference at all. This model only.
Distance for SINR.
No, but that's fine. I'm saying it's fixed SINR. That's a scaling issue, right?
Not necessarily. No, you know SNR for a distance.
Yes.
You don't know SINR for a distance. You
Just
take
pair
sum
by-
of SNRs based on distance versus sum of SNRs that you measure. And that's the difference.
Some of these NS2 models have that.
The
Doesn't
problem
care about the other interference.
That is the difference.
So
difference is in the sum of
right.
SNRs versus SINR.
Is it also because it has both disconnected and connected elements?
it has all of them have the disconnected as well as this connected region.
Hasbro's model for to calculate the arc, so same distance for the range model.
The calculation.
Yeah, how did you convert the distance into RSSI?
Okay, so basically what I did was I measured across the links to see what was the distance at which the RSSI fell below 5 dB. Okay, so when you do the measurement, when I did the measurement first, I don't remember the exact value, but whatever that value was at which the RSS or signal strength fell below negative 5 dB, that became the distance D for the distance-based model, and that also became the hop, the size of one hop for the hop-based model.
So the error here is calculated
Measured minus predicted. Right, so basically what's happening over here is measured is higher, but predicted is much lower. Right, so that's why they're giving us a very low accuracy over here. Similarly, I plot the links that were in the transition regions, and they take those links only to predict based upon each one of the models, and then estimate what is the error going to be. So again, the physical interference model is more accurate than the other models, even though links are in the transition region and the probability is only, the packet receive probability is not very deterministically measurable or predictable. So even though, so we clearly see that the PRR, so the physical interference model is better than other approximate models, and we really should move forward with a realistic model to get a better network protocol or algorithm in the future. So that's how I conclude from these experiments, set of experiments, that we see that interference power is additive, and the reason why I am emphasizing on doing the measurement to see whether interference power is additive is because there has been prior research, 2006 census, which says that interference power is not additive. And
my advisor had an interesting comment on that result. He said he's a hardcore power layer guy.
Right.
He said if interference is not power additive, I'm sort of going to eat my diploma. It's just impossible. I'm teaching students for years something that's wrong.
Exactly. So whatever they said in their measurement, I don't know how they found that out. Maybe the radio had a problem or the experimental methodology was incorrect. We had a different radio, but we had a better way of doing the measurements, and maybe that's why we are complying with the theory more than they did. They said that if you have 2 transmitters, or if you have 4 transmitters, you cannot say that for 2 transmitters the joint interference would be the sum of the 2 interferences, and for 4, and they also show a deviation in the threshold value. So if you increase the number of interferers, they say that the threshold, the 5 dB threshold which I was showing right now, was actually shifting to the right. But theory actually says that the threshold is actually constant. SINR threshold is constant. That is what we have learned from a long time. But they said that it actually shifts.
I think they have
They did. They had basically a single board computer with the Mica 2 modes attached to them. They used cable for battery, or I don't know whether they did not use battery, or instead of battery they used cable, or what they use it for. But the reason why they got a different result was, I'm pretty sure the measurement method was not accurate. They were trying to sample the received signal strength in the middle of the packet only, and only once, and the time synchronization in those modes are not good, and sometimes completely off.
So there is a capture effect. So that's
Yes.
But this is actually always work. If you want to put it in one sentence, it's perfect capture.
exactly.
Yes.
It's a perfect capture environment.
Yes. In fact, we saw the problem with the capture effect experimentally, that if you're receiving two packets, and the one that with higher signal strength appears or comes in later, then you miss both the packets. But if the one with the lower signal strength comes later, you would receive this higher signal strength. So it was very interesting to observe that experimentally.
But you see, that's not, I mean, depends on how you measure. The biggest problem is the measurement of RSS.
Yes.
And depending on how your hardware does it, you can make certain conclusions.
Right. But we were lucky that our hardware did it very accurately, because it was measuring the RSS continuously, averaging over 10 symbols, and for them they had to sample the ADC manually, or rather from the software, and that made a difference.
Well, so that's also a problem if you have, there are some issues. I mean, if you have uneven, things that are not perfectly aligned, or packets that are not of the same size.
Yes.
All those things pretty much make things much more complex.
Right.
You mentioned that in the census paper, the measurement was taken only in the middle of the packet.
Only in the middle of the packet.
More problematic than the 10 millisecond approach. You have implemented. Can you explain that further?
I did not implement the 10 symbol period method. It's already given to me from the radio. Or the 10 millisecond basically was,
But then every 10 milliseconds.
we are reading the received signal strength every 10 milliseconds. So you already have the previous 10 symbols.
Every
Average.
10 milliseconds, you read from the 10 prior symbols.
Yes, average.
From prior 10
From
symbols.
prior.
Yes.
So it's
That
just
means
adding
you're
to the
getting one.
Yes.
Getting approximately one reading per packet.
Uh,
Might be at the beginning, but depending on your synchronization.
Well, so basically, the receive is also synchronized with the transmission. So when I receive a command, although I'm the receiver, and I hear that there is a transmission going on, because I don't hear it after the transmission starts. I actually hear it when the transmitter is going to start, because I hear a command which says that the transmitter is going to start right now. Okay, so that's when I start my timer to calculate to measure the signal strength, right? So I'm absolutely sure that I will calculate the signal strength before the packet ends.
So 10 milliseconds after you receive the start.
Yes.
Press,
Yes.
you will read the register.
Yes. And
Means you're sampling
towards the end.
Towards the end of the
Yes, towards the end of the packet.
packet. And how is that better than sampling in the middle of the packet?
So the reason why sampling in the middle of the packet was not good was not because, okay, it could be nice to sample in the middle as well, but the reason why it was not good for the platform which in the census paper was because their time synchronization was not as accurate as ours. So it's possible that the middle of the packet which they're calculating is actually not even in the packet. So that is the problem.
Remember how they synchronize?
They did synchronization using beacons. I think they did that, but the clocks are very low granularity. Low granularity clock for them. We use a 32 kilohertz timer, so that the drift between the clocks is very little. It's actually tens of microseconds of drift, and the platform they worked on, the drift was about 7 or 8 milliseconds.
So that's the
So-
difference of using the telos
Yes.
mode versus the
Yes.
micro.
Yes, but the bottom line is that the measurement, the result was probably misleading.
So when you say that you actually know how is RSSI determined,
Right.
in the sense that it's 10 symbols average,
Mhm.
does it mean that you have the specifications text for the electronics?
Yes, I do.
So that's publicly available?
Yes, it is. If you look for CC24.
Zigbee
Yeah, you can download the data sheet pretty much. Just Google it and yeah.
When you say you had a multi-hop TDMA schedule.
Yes.
So did you compare the throughputs with other kind of schedules?
So basically, what was like over here when I said that the schedules were perfect. When I do the calculation, the schedule was perfect. Now, if I did compare that, but I don't have it in the paper because it was a trivial result. If you use a different scheduling model, for example, if you use a hop-based or distance-based model, they're conservative, right? So they will also give me perfect schedules, but the total throughput of the network would be much lower.
Why is this a trivial result?
It's a trivial result. Well, we know it. We know it's a conservative model, so it's probably going to schedule one link.
Like how much is the question?
No, I guess he's pointing out the different key topic, which is how best to schedule with a set of radio nodes.
Right.
And the centralized scheduling has certain performance depending on what algorithm you use.
Right.
Distributed would be better, but that goes up towards
To a different,
implementing
yes.
scheduling protocol and comparing it
differently, yeah. So whatever measurement or results which I got, and why I call it trivial is because it was centralized. First of all, I know I have the entire network given to me, and I'm simply using the links into the scheduler. By how much we can guess from the inaccuracy?
Your optimum is not trivial. You use some greedy algorithm.
Yes, of course.
It may not be optimum.
No, it's not optimum. It's greedy, but it's not optimum.
What
But
you mean by trivial is it obviously doesn't violate the scheduling constraint.
right. So basically, it's the same greedy algorithm. The input to the algorithm is just different when you have a different model.
If you think about distributed solutions, are you interested in that problem?
That is a very interesting
That's
problem.
the counterpart of this.
Yes.
That's a very
Yes.
hard problem.
It's a very hard problem, and thankfully I graduated before that.
Some distributed solutions. Zibin has
He has some heuristic.
partially.
So if you look at the Y-Media Mac, it's actually a hybrid between distributed TDMA and CSMA, and it's pretty interesting to study that as an example to look into a multi-hop TDMA, distributed TDMA.
Multi-hop when you have more constraints.
Right.
So your graphic is
Yeah, and you have a flow current constraint, so that's a different constraint.
the converse when working on scheduling centralized.
I've been trying to find a distributor.
Yeah, distributed is what you have to do because
Yeah.
centralized, it can be done. So yeah, what I want to do in the future was, well, this is how the home would look like in the future, which is Zigbee and 802.11, Bluetooth, cell phone, and wireless USB, everything put together in a home or office environment. How do we understand? Can we understand, or do they interact? How do we understand the interference between these technologies, different radios or multi-radio in a multi-radio platform? How do they interact with each other? Are they going to even work with each other? Because most of the companies which are working on these different technologies, they're working by themselves. They have not studied how the interaction is going to be. So it's very interesting to see, is the SINR model going to look any different? Is it going to look same, or how do we profile such a network so that we can benefit in the future? So that there is a better cooperation and coexistence between different technologies. So how would the physical interference look like? Can we do a measurement-based interference model? And can we design protocols that improve the coexistence? Another thing which you might have noticed, that looking at this graph in which there's a green curve which is very good and the blue curve which is not very good, is it useful to have a middle layer service which would change the threshold, the SINR threshold in the MAC layer, depending upon what kind of application it's looking at. So is it a low latency application? It's okay to do retransmissions. So should we use the transition region, or is it an error tolerant network and we should not it's a low latency, and we should use the connected region, and if it's a error tolerant network, should we use the transition region just in order to be able to transmit more data. For example, in a video application, it's okay if we miss a few frames, so is it okay if I do the error tolerant threshold in the MAC layer? Other things that a middle layer service can provide is, it might have a directional antenna or a transmission channel, a different network interface, choose a different network routing mechanism and thresholds. Given all these things, can I tune these parameters using a middle layer service depending upon what my application wants? Would be an interesting thing to study in the future. Okay. So questions?